Hello students, welcome to Educate. In the last video, we have discussed till ionization enthalpy of transition metals, chapter 4. Now, in this video, we will discuss about trends in the M2 plus / M standard electrode potentials. In the chapter of electrochemistry, we have discussed what is standard electrode potential. Just again, I am telling you some concepts which will apply in this topic. So, standard electrode potential means reduction potential, means the ability to take the electron. That is the meaning of standard electrode potential. As the name indicates here, as you can also predict, here is M2 plus / M. That means what will be the ability to undergo from oxidized form to reduced form. That means from oxidized form, that means M2 plus to atomic state. What will be their ability? About that we will discuss in this topic. So let's see here, I am here zooming this graph here, and then after you watch out carefully. Let's see. Generally, as you are observing here, as we move across the period, the standard electrode potential is getting less negative. Here, -2, -1.5, -1, -0.5, 0 and 0.5 here. So you are watching here that on moving across the period, the standard electrode potential of M2 plus / M is becoming more positive and less negative. And I have told you, if negative be the standard electrode potential, if standard electrode potential will be negative, that means that element will have greater tendency to get oxidized compared to that of hydrogen. If any elements will have greater standard electrode potential, that means that element will have greater tendency to get oxidized compared to that of hydrogen. Here, as you are moving across the period, that time the standard electrode potential is becoming less negative. Less negative means value, if you tell about the values, then values is here increasing, but that became less negative. Like that, same here, this is the only difference of literature, that is among -5 and -3. -5 is more negative than -3, but the value of -3 is greater than that of -5. Okay, so as you are moving across the period, the standard electrode potential is becoming less negative. That means that is their oxidized form will be less stable than their atomic state. That means here standard electrode potential is becoming less negative. That means M2 plus will have greater tendency to undergo in atomic state. That means here the element will have greater tendency to remain in the atomic state than that of the oxidized form. Okay, in ionic state here. This one. Now there is some exceptions about which we will discuss. First exception comes at the manganese. Then after here at nickel. One point here about the copper and that of the zinc here. Okay, here cobalt also, but here about that we will discuss later on. That's not in your syllabus. These are in your syllabus. So about that I am discussing. So firstly, let's see about the standard, about the copper. Copper here, the standard electrode potential is positive. 0 is here, and a standard electrode potential of copper Cu2 plus / Cu is this much. That means here the standard electrode potential of copper Cu2 plus / Cu is positive. Okay, below that the standard electrode potential of other elements are negative here. That means these elements will be stable in case of oxidized form, and the copper will be stable in atomic form. Okay, so what's the reason here? What's the meaning of that? That means among the copper will have less tendency to be in oxidized form. That means in Cu2 plus state compared to that of hydrogen. That means the copper will have less tendency to be in +2 oxidation state compared to that of hydrogen. And that's the reason copper do not displace hydrogen from the acid. Like copper, when you will react with HCl, even though conc HCl, then no reaction will take place. Okay, you might be think that why here copper is a metal, as in other case we are doing copper will displace the hydrogen and form CuCl2 and hydrogen. Other elements is doing, but why not copper? So that's the reason is because the standard electrode potential of Cu2 plus / Cu is positive. That's why copper here, among copper and hydrogen, copper cannot go in the oxidized form. Copper cannot displace hydrogen, and hence this one. That means copper will not react with conc HCl, but copper reacts with the concentrated sulfuric acid or the concentrated nitric acid. What's the reason here? Its reason is different. Why that happened? Let's see here. Actually, H2SO4, conc H2SO4, that dissociates into H2O, SO2 and nascent oxygen. This nascent oxygen, and the reactivity of this nascent oxygen will be very high. So this nascent oxygen combine with copper and then after form CuO. Then after this CuO react with H2SO4 and then after form CuSO4 and H2O. Overall reaction will be here. You have to firstly balance that. So 2, 3, 4 already balanced here. This equation is balanced, this equation is also balanced, and this equation is also balanced. So then after CuO and Cu, that means here CuO which has been formed during the reaction, that has been consumed also. So no formation of CuO. Here nascent oxygen which has been formed by the dissociation of H2SO4, that has been utilized here also. So no, that will not form. Then here balanced chemical equation, copper react with 2 moles of H2SO4. There will be formation of CuSO4, 2 moles of H2O and 2 moles of H2O and SO2. Okay. So this is here. That's the reason copper don't react with the HCl, because the standard electrode potential of copper is positive. That's why it cannot displace H plus from the acid. It cannot displace hydrogen from the acid. That's why copper don't react with HCl, but that can react with H2SO4. Okay. Now, same we will discuss about why that react with HNO3. In the same way, HNO3 that will dissociate into H2O, NO2 and nascent oxygen. In some case, depending on concentration here, HNO3 can also dissociate into H2O, N2O and nascent oxygen. During that case, you will have to, depending on condition, what's there. So, let's see, I'm taking only this example. It's not too much concentrated here, HNO3. So, HNO3 dissociate into H2O, NO2 and nascent oxygen. Now, copper will react with this nascent oxygen. Firstly, balance that 2, 3, 4, 3 here. So, 2 balance here. Now, this one is balanced. So, copper will react with this nascent oxygen, form CuO. This CuO will react with HNO3, formation of CuNO3 whole twice plus H2O. So, firstly balance this equation. Here this one is balanced. This equation is balanced. So, overall reaction. Here nascent oxygen which has been formed, that has been consumed also. Got out. Then after the CuO which has been formed, that has been utilized. So, got it. Then after here, copper here, this react with 4 moles of HNO3. 4 moles of HNO3. As a result, there is formation of this is the overall reaction. I hope you understood this one. This one is not in the NCERT book, but why that happened, there is. So that's why I have taught you why the Cu copper don't react with HCl, but that react with H2SO4 as well as with HNO3. That means the copper react with oxo acid, means the acid which contain oxygen. That means the acid which contain oxygen, and after their dissociation will give nascent oxygen. Nascent oxygen means newly formed oxygen. Anything called nascent phase, in nascent stage. Like this YouTube is right now in nascent stage, means the formation of this YouTube channel has not been taken a long time. Okay, so that is nascent oxygen. That's done. Now let's see here that firstly I taught you, if on moving across the period, the standard electrode potential of the transition metals became less negative. Reason is that as we move across the period, the ionization enthalpy, the first summation of first and second ionization enthalpy, the ionization enthalpy for M2 plus will increase. So there that the metals will have less tendency to be in oxidized form compared to that of in atomic state. So since the ionization enthalpy for +2 oxidation state will increase on moving from left to right. That's why these elements, the transition elements, show less value or less negative value of their standard electrode potential. Okay. Now let's see. Then after dip is observed at the manganese. You are watching here manganese. Here at the manganese, tremendously there is fall in the standard electrode potential. What's the reason here? Now goes to the electronic configuration of manganese. The manganese electronic configuration is this one. And I have taught you the second ionization enthalpy of manganese will be very less compared to that of this element. How's? Again, I am going on that concepts. Let's see. So firstly, the electronic configuration of manganese is like this. This one is electronic configuration. Okay, in this one case, firstly the electron will enter in 4s and then after will enter in 3d. But when electron will have to lose, then electron will lose from 4s because fourth cell is the valence cell. So electron will release from 4s. So in +2 oxidation state, its electronic configuration will be 35 here. So this d orbital in manganese, in d orbital, in d subshell there be 5 orbital. In d subshell there is 5 orbital and d5, that means all these orbitals, all these 5 orbitals of d subshell that are singly occupied. That means these orbitals are half filled. And half filled orbital as well as the fully filled orbital provide extra stability. So Mn2 plus is stable. So Mn2 plus is stable because manganese in +2 oxidation state contain half filled d orbital which will provide extra stability to the Mn2 plus. So that's why the manganese will have higher tendency to be in +2 oxidized form. So its standard electrode potential has become more negative compared to that of the other elements. Okay. Then after increase about the cobalt, you will not have to study about the nickel, copper and zinc. This one. About the copper we have discussed. Now let's see about the nickel. What happened in case of nickel? Nickel, this one, when it will undergo in oxidized form, Ni2 plus, atomic size, ionic size will be very less. The ionic size of nickel will be very less. So Ni2 plus when comes in the aqueous state, then high magnitude of this water, when the Ni2 plus will surround by this water molecule, then high magnitude of heat energy releases. That magnitude of heat energy releases, that is called hydration enthalpy. When Ni2 plus will be surrounded by water molecule, when Ni2 plus will surrounds by the water molecule, then high magnitude of heat energy releases. That means the hydration enthalpy of Ni2 plus is highly negative. So how much heat energy released from the Ni2 plus? That will cause the release of electron from the another nickel atom. Here when Ni2 plus will surrounds by the water molecule, high magnitude of heat energy will release from there, and that magnitude of heat energy will cause the release of electron from nickel atom. So due to high hydration enthalpy, it have greater tendency to be in oxidized form. Okay, so here energy is available to release the electron. So Ni2 plus, so among nickel atom and nickel ion, the nickel will have greater tendency to be in Ni2 plus in oxidized form. So that's the reason here the nickel, in case of nickel, the standard electrode potential is more negative than expected. Is more negative than expected. Okay. And then after among zinc also. So when you consider about the zinc, same as in case of manganese, the half-filled orbital here, when you will write the electronic configuration of Zn2 plus, so that will be till here and 3D 10. 3D 10 here. So d orbital is fully filled. D orbital is fully filled. So it will provide extra stability to the Zn2+. That's why zinc will be more stable in +2 oxidation state. So it will a standard electrode potential. So that's why the standard electrode potential of Zn2+/zinc, that will be more negative than expected. Okay, copper here is positive. So you mean wherever you have seen the exceptional behavior, the reason we have discussed, just I am mentioning you once again, where there is exceptional behavior. One is a standard electrode potential of manganese Mn2+/Mn is more negative than expected. Okay, in the short you may write that here, goes down half filled. Why? Half filled d orbital. That's the reason here. And second one is a standard electrode potential of Ni2+/nickel, that is also is more negative than expected. Reason is high hydration enthalpy. Third exceptional here, third one is point, the standard electrode potential of Cu2+/Cu is positive. Why? Okay, here reason. What's the reason here? What is the reason here? The hydration enthalpy of Cu2+ here is not too much high. This means hydration enthalpy is not too much high, but ionization enthalpy is very high. Ionization enthalpy is high. Hydration enthalpy here will not overcome the ionization enthalpy. That means here Cu2+, suppose here is Cu2+. When it will surrounded by the water molecule, then heat energy releases. And that heat energy released is called hydration enthalpy. This one is called hydration enthalpy. From here, energy release, and here is another copper atom. But this released energy is not sufficient so that it will cause the release of electron from the copper atom. The hydration enthalpy of Cu2+ is not enough for the release of electron from copper atom. That's why hydration, this one standard electrode potential of Cu2+/Cu is positive. So here reason it's here is, what's the reason here? So the hydration enthalpy. That is here. Now then let's see about the zinc. Fourth one is the standard electrode potential of zinc is more negative than expected. So fourth exceptional here is the standard electrode potential of zinc, Zn2+/zinc, is more negative than expected. And what's the reason here? Fully filled d orbital. Okay, guys, which I have taught you in this one, only meager is outside from the NCERT, or almost all of them is in your NCERT, but that has been not written so that the normal students could understand that concepts. So this one is here. One point I am telling you, which I have repeated a number of times, that in your IIT main examination as well as in a NEET examination, more than 90% question will ask from NCERT book. But you will have to develop the technique to solve the questions of IIT as well as of the NEET examination. So here everything is written which I have taught you, but that's in the different manner. And so if you will study like this as I have taught you, very easily you could solve the questions of IIT as well as NEET. Actually what happened, a number of students as well as the parents also, I am not only telling about the students, but a number of parents also, they don't believe that the questions in IIT as well as NEET ask only from the NCERT book. Because because question will ask like this one, which I have taught you in this manner, and that has been written in the NCERT book in concise form. So they think that questions usually don't ask from the NCERT book, but it's a fact that more than 90% questions asked only from the NCERT book. Okay, like this, if you will study, very easily you could answer the questions of IIT as well as of the main examination. This was graph. Let's see about the questions. Now watch out this question here. So a question is why Cr2 plus is reducing and Mn3 plus is oxidizing. So in the other way, the question is asking that chromium Cr2 plus acts as reducing agent while the Mn3 plus acts as oxidizing agent. Its question is asked, and all of you know that most of the phenomena in case of chemistry based on the electronic configuration, because the valence electron usually participates in the reactions. That's why here we will have to firstly write the electronic configuration, and then after we'll have to think over that. Okay, so firstly write the electronic configuration of Cr2 plus. So firstly write the chromium electronic configuration. Chromium atomic number is 24, and in this case I cannot say do anything, that you will have to mug up. I have taught you Scotty, VCR, May, Pheco, nickel, copper, zinc, and to get the atomic number of these elements, scandium 21, then after titanium 22, and like that you will have to go through that and you will have to mug up. Scotty, you know already. VCR, that's also you know. Scotty, VCR, May, Pheco, nickel, copper, zinc. So atomic number of chromium is 24. This is the electronic configuration of chromium. So let's see the in +2 oxidation state, what will be their electronic configuration. So one electron will reach from 4s and one electron from 3d. It acts as reducing agent. Chromium here is acting as reducing agent. That means chromium will have the tendency to get oxidized. Cr2 plus here is acting as reducing agent. That means chromium Cr2 plus will itself oxidize. So let's see in the oxidized form, that is in +3 oxidation state, what's it? Electronic configuration. 3d3 here. Now what is here, in the previous class also I have taught you, and that concept will also comes in the coordination compound, the next chapter. What I taught, and this one name was dxy, dyz, dxz, dx square minus y square, and this orbital is dz square. The degeneracy, all the orbitals are degenerate orbital. That means the orbital of the same subshell are degenerate. Like in p orbital, there is px, py and pz. The energy of all these three orbitals, px, py and pz, will be same, but their orientation will be different. Px will be in along the x-axis, that means here this lobe, this one will be in this axis. Py means suppose this is y-axis, and so its lobe will be along the y-axis, so it will be called py. And pz, suppose this is z-axis and the lobe will be along the z-axis, so it will be pz. So but the energy of all these three orbitals will be same, but their orientation means direction is different. In the same way, dxy, dyz and dxz, I should tell you. Okay, let's see here. Yes, let's see. A small diagram I have drawn. Here it's x-axis, x dash, y-axis and y dash. So dxy means one lobe will be, and you already know that p orbital have dumbbell shape and the d orbital have double dumbbell shape. Means two dumbbell will be there. dxy means one lobe will be along this one and another lobe will be along this one. So in xy coordinate that will be dxy, same dyz and dxz you can draw by yourself. Dx square minus y square means here, dx square minus y square means this one x-axis and this is y-axis. So one lobe will be along the x-axis and another lobe will be along the y-axis. So this orbital is dx square minus y square. And dz square is what? This is the origin from where the x, y and z, all the orbitals originate. So for the convenience, I am taking only one orbital, one axis. So here is the origin. This one, it is x, it is z, not y, okay? Z here. So one lobe will be like that, and another lobe will surround around the origin, this one. Okay, so that is dz square. Go to that. This one will be utilized in the IIT main as well as in NEET examination. That's why I have taught you about this concept. But who is preparing only for the 12th board examination? These concepts will not harm to them also. That will be easier to understand to those guys. Let's see. So the degeneracy of this d orbital do not maintain. The energy of dxy, dyz and dxz, that will decrease, and this energy of these orbitals will increase. That will be called T2g energy level. And the energy of dx square minus y square and dz square, that increase, and it will be called Eg energy level. Here in case of Cr3 plus, there is 3d3. This 3 orbital, 3 electron will be in T2g energy level. So in T2g energy level, it is half filled. Chromium will contain half filled T2g energy level in case of Cr3 plus. Chromium will contain half filled T2g energy level in plus 3 oxidation state. So obviously Cr3 plus will be more stable compared to Cr2 plus. So here Cr2 plus will have the tendency to undergo in Cr3 plus. Okay, in chromium, in plus 3 oxidation state, chromium here will contain half filled T2g energy level. That's why the chromium will act as a reducing agent and itself get oxidized. So Cr2 plus will have the tendency to get oxidized, and that's why it will act as reducing agent. Now let's see about the manganese. Let's see manganese. Electronic configuration here, manganese in +3 oxidation state you will have to consider. So manganese here, write the electronic configuration, atomic number of manganese 25. So electronic configuration will be manganese when getting oxidizing, so it acts as oxidizing agent. So it will undergo in reducing state. So when it will undergo in reducing state, so that will undergo in Mn2 plus. So let's see the electronic configuration of Mn2 plus. Because here from manganese the electron will release from 4s, since 4s is the valence shell. And let's see, consider about the electronic configuration of Mn3 plus. So manganese in +3 oxidation state have the outermost electronic configuration as 3d4, and here the valence orbital of manganese is 3d5. So obviously Mn2 plus is more stable than that of Mn3 plus. So Mn3 plus will have the tendency to undergo in +2 oxidation state. Mn3 plus will have greater tendency to undergo in +2 oxidation state, because in +2 oxidation state the manganese will contain half-filled d orbital. Therefore the manganese will have Mn3 plus will have the tendency to get reduced. So Mn3 plus when have the tendency to get reduced, then it will oxidize to other element. So to other element, when it will oxidize, so it will act as oxidizing agent. So instead of Cr2 plus and Mn3 plus, both contain 4 electron in d orbital, even though chromium Cr2 plus act as reducing agent, while the Mn3 plus act as oxidizing agent. Okay guys, clear? And here, don't consider that inorganic is to mug up. If you will think, you could solve the questions asked from the inorganic chemistry very easily. If you will try to mug up, then you will tell that, oh, chemistry is too much difficult. That's actually very easy. But you will have to think, not have to mug up. Now let's see the next question. Let's see. About this reason I have taught you. Okay. So no problem here. Then after, let's proceed. This topic, let's see. Trends in M3 plus less M2 plus standard electrode potential. What's the meaning here? It means that what will be the ability when the transition metals is in +3 oxidation state, then what will be their tendency to undergo in +2 oxidation state. About that we will have to consider. So let's see from here elements written here. Just here, watch out where there will be exception. Scandium stable in +3 oxidation state because that will acquire noble gas electronic configuration, so it will be very high. No exception from there. Then after consider about the here manganese will be in +2 oxidation state. It is more stable, so that will be less negative. Then after let's see come about the iron. Iron here in +3 oxidation state, it will contain 3d5 half-filled d orbital. So the oxidation of iron have greater stability in +3 oxidation state compared to that of +2 oxidation state. That's the reason the standard electrode potential of Fe3+/Fe is more negative than expected. At the magnesium you came. Then after about let's see about zinc here. Zinc is highly stable in +2 oxidation state. So it will not show +3 oxidation state. So when it will not show +3 oxidation state, then it will be less negative than expected. So a standard electrode potential of Zn3+/Zn2+ is less negative, and that will be positive actually, negative than expected. One point here left is about the vanadium. So here in vanadium. So vanadium, atomic number 23, 1s2, 2s2. This one. So what happened here, in +2 oxidation state, 2 electron will release from 4s, and 3d orbital that is containing 3d orbital will contain 3 electron. That means here T2G energy level will be half-filled. So when T2G energy level is half-filled, that means vanadium is more stable in +2 oxidation state. So if vanadium have undergone +3 oxidation state, that will have high tendency to come in +2 oxidation state. So that will be less negative than expected. That is here. Or the value will be less. Okay. That means here reduced form is more stable. So that will be more. That is here. Very easy. About that, we have discussed about the standard electrode potential. That means one is here about the standard electrode potential from +2 oxidation state to atomic state, standard electrode potential that we have discussed, as well as we have discussed from oxidation state of +3 to +2. In the next class, we will discuss about trends in stability of higher oxidation state. Trends in the stability of higher oxidation states. From there, about the halide and that of the oxide, we will discuss in the next video. It's all for this video. Thank you, Team Educate.